So I wanted to achieve maybe three things today. Talk about what the questions might be. This is something that will go live, I guess, after we've had this discussion and recorded it and placed the YouTube link in there. I will go through a minimum set of equations, maybe, that you need to be able to do what you need to do, which is written here also. And then go through the stuff that's online, which is really the same material as previous years, this kind of short, maybe 20-page booklet of things, which is kind of standard, but you can probably figure out from the equations we talk about what will and won't be in there. Anyway. So the three questions you'll see here, I mean, it's the same protocol as other times. But these are the three components. I guess you can all see that, right? The material is 4.2 to 7. So you remember that 4 and 5 were Bernoulli. 4.1 was accelerations of static fluids, which is why it's not in there. That was on the last test. This is all the stuff that would have finished last Friday, 7.3, or the third class of week 7. And so I think 4 and 5 are Bernoulli, basically, both linear and along a streamline and perpendicular streamlines. 6 was conservation of mass, and 7 is conservation of momentum. So those are the subjects, and you know that. And so I never think of it in terms of chapters in the book. I think of it in terms of weeks in which we spent doing things. 3 questions. They're all equally weighted. Again, 110 points apiece. 100% is 100 out of 110. They all involve Bernoulli. So that's perhaps not surprising, since that's kind of a staple of what we do. First one is Bernoulli and cavitation. The second with Bernoulli, conservation of momentum, static conservation of momentum. And the third being Bernoulli, conservation of momentum and movement control volume, and ideal gas. So those are the things that you should know. Okay. And so you can work out from that what you don't need to know, and you can probably surmise from what we talk about the individual expressions. So there's a short sheet of expressions that perhaps it's worthwhile knowing. So any questions before we leave this? You'll see this recorded, and you'll get this, I think, tomorrow morning, or if not before. No? Hearing none, I'm going to move to notability. Okay, I was going to do this. So if you didn't get it down, you'll be able to grab it. Well, you don't need it. You'll be able to print it from what you get later on today. All right. So, the things that you might want to, which will hone your thoughts. So the first is gas law. You know that pressure is equal to density gas constant times temperature. You know that pressure has to be absolute. You know that temperature has to be absolute. You know that this, since density is written as a mass per unit volume, you can also write this as a mass per unit volume, RT. So remember that temperatures and pressures, importantly, always have to be absolute. Pressures especially, importantly, right? Say it again, sorry? No, pressure, no. Well, you could multiply this by a volume and get rid of this, if you wanted to. So no, so this is just the fact that this term here is density. Mass over volume. So that's all that is. That's substituting for density. you know that, well, you don't know, you know that the vapor pressure, which is mentioned in the first question, is equal to where this transition occurs from a liquid to its vapor. And for water, it's something of the order of 2 kPa. Atmospheric pressure, as opposed to absolute, is about 101 kPa as an absolute pressure, but it's obviously zero pressure as a gauge pressure, and you know those differences. So you've seen that before, so I think you're familiar with that, I hope. Okay, so that's maybe stuff from your previous existence, but you know that stuff. We know from weeks 4 and 5, we know Bernoulli. And we have it parallel to streamlines and perpendicular to streamlines. We know that it occurs in some kind along a streamline or along a stream tube. We have talked about why we write it between an upstream location and a downstream location for what we've done with power losses. But if there's no loss, which is implied in certainly the 4 and 5 week stuff we did was in viscid fluid with no losses in the system, then it doesn't matter where you write it, upstream or downstream, but it's good to write it, just get in the habit of writing it the particular way it is. And you know the way I always write it is pressure upstream, an elevation head upstream, and a velocity head upstream, and it's equivalent to the same downstream, or the same components. If a jet is coming out, typically the pressures would be 0. You know, we will talk about free jets and other stuff today, maybe. But we've talked about this stuff coming out here. You know, if you take the pressure here, then the pressure is atmospheric pressure. For the reasons that we talked about of fluids, the lateral pressure acting on this jet here being atmospheric pressure, and therefore since fluid pressures act the same in all directions, then inside the jet it's essentially 0 atmospheric pressure as well. Elevations are always measured vertically positively upwards. Positive in this direction. Fluid pressure is positive. Velocities are always streamline velocities. They're not the vectoral components. So these velocities are always a streamline component. So this is a positive velocity, and this is a positive. Always positive. It's never negative velocity. Okay. If we look at the behavior where we've done something. We've done some examples of things going over a bump. And these being 2 different streamlines. Maybe you have a different streamline here. Then we can also draw something which is the normal to this boundary, and we can move from some location, from one location, I guess it would be point 1 to point 2. And the appropriate equation would be, in this particular case, how do we usually write it? Well, we can write it again, P over gamma. We've written it perhaps slightly differently. We can write it as 1 over gravity times an integral v squared over r dn. Plus, I guess, elevation equals constant. And so you can write it between 2 different points, and we did an example with that. And so I guess the important things in this are that the pressures, so I guess we could write it, maybe just to not confuse things, write it. So this would be pressure at location 1, elevation at location 1, pressure at location 2. This is gravitational acceleration, v squared over r dn plus elevation at point 2. And I guess in this, so pressures are the pressures at those particular locations. Elevations are the particular elevations at those locations, following this same sign convention we have here. The velocities would be the streamline velocities at these points. So this would be v1 in this particular case, and this would be v2 at this particular case. And and the radius would be the radius of curvature. So whatever, if you were to draw, let me do this. You might not absolutely need to use this, but you can write it down anyway. And so the radius is the radius to that point from here, so it would be the limb. And n is the direction of the outward normal. And so if n is in the direction of z, as it is in this case, then dn would equal dz, which it certainly is here. Then you could substitute this as dz and do the integration. We did that before. I'm not sure whether we've had a streamlined question on an exam. I'm not sure we have one this time. But anyway, you need Bernoulli as a general set. Okay. We know that sometimes we've used, in the context of Bernoulli, we've used continuity, which is also conservation of mass. And so you'll recall that if for this expression you have two unknowns and you need to solve it, then you can always often link it by linking the upstream velocities. And so conservation of mass for Bernoulli is just that the velocity upstream times the area upstream is equal to the velocity downstream times the area downstream. Times the density, I guess, as well, which usually doesn't change. But usually you can get away with just using the areas and the velocities if it's an incompressible fluid, such as a liquid. Okay? So that's that. Any questions? Do we go down the road on this? Yeah, go ahead.
With a normal n, should be pointing towards the center?
It should be pointing in the. It's the direction. N is always, the sign convention is always that n is in the direction outwards from the radius, the center of the radius. So n at this point here would be in this direction. It gets a bit complicated here because now it's at an angle, but certainly if it's vertical, then n and z are equivalent to each other. I guess if you were going, yeah, so that's on the radius. Yeah. Yes, sir.
What would be like an example of one where you have to include the densities, like if there's two different fluids in the same tube? I mean, they'd be mixed, so how would you see the two different densities?
For this in the continuity equation?
Yeah.
So it could be, for example, a case where you have a decapitated tank, where there would be fluid coming out of a tank that's under pressure and therefore is quite dense, and it comes into the atmosphere where it would be a different pressure and therefore less dense. Okay, good question. Yes? Can you shout, please?
The radius
it's different. It's the length that it takes to get to this point. So this would be R1, and this would be R2. Okay, great. All right. Don't sweat too much the perpendicular streamline one. All right. Still red? Okay. So we used Bernoulli to get the equations for free jets. The example I think we looked at was something that was like this. And you know that to use Bernoulli, the idea is just to have a streamline that goes through an upstream to a downstream location. And without deriving it, what do we use? We use the big reservoir assumption. So velocity V1 equals 0. The pressure at 1 is 0. The elevation at 1 is equal to h, if we choose a datum that is here. And we know that equivalently the velocity at 2, well, we don't know. Because the fluid is coming out at that point and it's atmospheric around it, we know that the pressure is atmospheric, and we know that the elevation relative to our datum is this. And if we take those and we use Bernoulli, we get that the velocity is equal to square root 2gh, I believe. It also turns out that as we go down through this jet, and if you look at a height that's different, I'm pretty sure it turns out that the velocity at the lower point, which may be 3 if you write it, is equal to square root 2. You can use Bernoulli again. Different h this time. It's equal to the total height of this. And that's just due to the fact that it's the same as it's free falling. And so you can calculate what the velocity is as a result of that. So we spent some time talking about free jets. And so that just comes directly from Bernoulli. It doesn't matter if it's squirting out of the side of this container, it would still be the same velocity. So in other words, if you had this, bless you, if you had a hole here and it was coming out through this hole, you could derive the same expression, and you would derive the same expression. But the velocity is a streamline velocity. So it's not necessarily a vertical velocity. If it's directed horizontally, it's a horizontal velocity that comes out with. But that comes out of Bernoulli. So I guess to reiterate, the velocities you get from Bernoulli are always in the direction of the streamline, and actually also clearly in this, they're also the direction of the streamline as well, because the velocity perpendicular to the streamline is 0 by definition. So anyway, so free jets. We talked about two conservation equations. Conservation of mass, which we'll talk about first. Any questions on free jets, by the way? No? All right, conservation of mass. We have two terms. We have an accumulation term. So if we talk about a volume, we talk about x and z maybe. We talk about velocities and a volume and volumes. Always use this through bar for volumes. So the accumulation term is, if we want to write it out, rate of change with time of the product of density and volume, which if we split up by the product rule is just rate of density times rate of change of volume plus volume times rate of change of density is equal to the sum of the mass flow rates. Mass flow rates are equal to velocity normal to the boundary times an area times a density. And so that's always worthwhile doing. Let me rewrite that as this velocity being a velocity w rather than a v for reasons that will become apparent. Because we've used this analog that the velocity to a static observer is equal to the velocity of the control volume plus the velocity of the jet. So if you like, that's just going to complicate matters. Let's just explain it. So this is the velocity relative to the control surface. This is how quickly the control volume is moving. I think we've drawn it like this before. Or control surface, control volume. And this is how it looks to a static observer. So if you looked at the videos, the fireboat, water coming out of the hose on the fireboat, 1 meter a second, the boat's going at 1 meter a second. To a static observer, you see that water going at 2 meters a second. The boat's going at 1 meter a second in the x direction. It's squirting out in the x direction at 1 meter a second. The velocity to a static observer sitting here is that it's going at 2 meters a second. And so you have to remember that. And so this W that goes in here is always relative to the control surface. Probably the best way to think about it. These are changes in volume as a function of time. And so I suppose the analog for this would be a constant volume, I suppose, would be filling up a tire where the density changes as a function of time because the tire is the same volume and the pressure is increasing as you pump gas into it. And this would be a case where the control volume is changing, such as a balloon getting larger for basically the same volume, same pressure rather, this in the system. Or, I don't think you need a very complex control volume look for the things that we're doing. But anyway, so conservation of mass is defined in this. And we'll go through, I'll try and point you to the examples that you might look at. Any questions on conservation of mass before we move ahead? Yes?
What's the difference between the control volume and the control surface?
Yeah.
Just where it goes in and comes out.
No, the control volume is that, so the control surface is what's attached to the outside of the control volume. So there's a rigid control volume, in which case the control surface will be moving exactly at the same rate as the control volume, which would be a box, solid box, or a balloon which you're inflating. As you're inflating and also moving, they'd be moving at different velocities. So the back of that balloon will be moving at a different velocity from the front of that balloon because it's getting bigger over time. Right? So you can imagine the back of that balloon not moving at all, so that control surface will be not moving. The front of the balloon would be moving because it's expanding, and the control volume would be moving maybe at the center of that balloon at half the speed of either of them. Okay? And there were some examples done, but I think that's more complicated than you'd need for a test, if that helps. So, right. Any others? Okay. So conservation of mass was one, and the second was conservation of momentum. And so in its simplest form, it was all steady state that we do, and in its simplest form, it's equal to W plus velocity of the control volume. And we always used a rigid system, so the velocity of the control volume was always equal to the velocity of the control surface. So in other words, a rigid box that's moving, not a balloon that's inflating at the same time it's moving. Multiplied by mass flow rate, is equal to the sum of the forces. And typically, these would be, there's three potential components, right? So this is just a single equation that has scalar quantities in it. But these are components which are in the x, y, and z directions. So typically you'd resolve in one or two directions to be able to figure out what's going on. So this might be resolving forces in x, and then these would be the components of mass in that direction as well. These are all vectors, but you can think of them as individual components. So what is this? This again is the velocity across the control surface. In other words, the speed of the water coming out of the hose. And this is how quickly the boat is going. Of the control volume. And I think the same applies here. I'll write it out. So V static equals W plus V CS. These are vectors, of course, right? They're X, Y, and Z components, but typically you're only interested in one at a time. And I suppose the important things, which actually I didn't mention in conservation of mass, you must know it already, is that it's positive if it's out, and it's negative if it's in. That's always the case. That's certainly the case here. Same sign convention. But these, importantly, are always related to the global axes. And so if we looked at a control volume here, and we looked at x and z, positive upwards, then this velocity would give a positive velocity in here. So in other words, if this control volume was fixed, then this velocity would be positive here, and if it's coming out, it would be positive here. But the mass flow rate would be in, and so it'd be negative, and the mass flow rate here would be positive. So these are always the Cartesian coordinates. If it's static, of course, you can just neglect this term, and this is the velocities across the control surface, and you only have one term. But there's a difference. There's a sign convention involved in these. That's important. Okay. We'll go through an example, or we'll touch on an example. Okay. So remember the sign conventions. Mass flow rates are always positive out, and the reason is it's positive out is because this unit normal, if you recall, is parallel to this, so the dot product of these two is 1, and so it gives unit value. In this case, the unit normal is in the opposite direction, and because this is really, we've written it in a simplified way, it's a dot product that we're using here, that this is the reason for this becoming negative, because it's going against the outward normal. The velocity is in the opposite direction from the outward normal. Okay? Anything else? Okay. So we're halfway through. There's one equation also you'll be given on your sheet, which means that you probably will need it. Actually, you won't be given this one, but you know it, right? Newton's second law, you know. It's a vector, but it's resolved in each of the directions. And I guess the other thing that's worthwhile knowing is that velocity is equal to change in location with time, which means that location is equal to velocity times change in time. Velocity, you won't recognize it, the derivation from this course, but you recognize it from your dynamics course. Velocity is equal to an initial velocity plus acceleration times time, which is equal to v0 dt. You only need the result of this, not this derivation, plus at dt. And if you integrate these, you get x equals v0t plus a half at squared. You recognize that expression, right? And that may be useful as well. We talked about it in some of the questions that we've done, and so you might recognize its use. So no implied guarantee, but I think if you know how to use these equations, you can probably do okay. I think you might even need to know less than these equations and still do okay. Right? So I'm sure you can take hints. Right? So any questions before we go through some examples? No, everyone's so quiet. All right. What else do we have? I guess. So I realize there's lots of stuff to look at, and so we can go on forever about materials. So given those expressions, maybe I will linger on certain things and not linger on others, and you can probably take that for granted. So manometry, I didn't mention manometry, but certainly you can use Bernoulli to get manometry, right? If you have a static fluid and you wrote Bernoulli between a location here and a location here as 1 and 2, and the velocities are 0, you'd find out that you got exactly this expression. And so that's old school for you because you've done that. We talked about Bernoulli. And we talked about specifically about along a streamline. You can write it in different ways. I tend to write it this way, but it has the same equations in its integrated form, I guess. We've also talked about it in its differential form, but I think probably you only need it in its integrated form. I think you know how to use it. You've used it in multiple cases. We've talked already about free jets this morning, and how you get the equation for free jet, which is this expression here, by writing it between 2 points. You probably are quite familiar with the big tank. The expression large tank, large reservoir, means the velocity in that reservoir is 0 or approaches 0, and you can use that to make your life a bit simpler. Otherwise, you'd end up with an extra term in here that you'd have to accommodate. So using this value of v1 equals 0 makes it easy, and you get this behavior here. Yeah. So this expression, this is a free jet also, and so I think we did this. I'm pretty sure we did this one in class. And I guess the other kind of the psychology of this as well is that, so you've looked at some things online, you've seen some things in class. Certainly when I put an exam together, I'm much more familiar with the things I talked about in class than the things that are recorded online. And just because I might not have looked at them so quickly, so recently. And so that might guide you as well in terms of the things that you think about. we did this example in class for sure. And the basic question here was, how high is this? How high does this jet reach? I know that we talked in class that if you had an exit point here with a nozzle going out of here and something going up here, then we could show that the height to which this would rise would be equal to the height of the tank. It's not the case if it's directed this way, because it has some direction. You could imagine that in the limit, this horizontal hose being horizontal, then clearly it can't get to this height ever. But it's trying to aspire to that, so it's directed. And so if you remember the essence of this, there were two ways to be able, you could do this in two ways, I think. The question basically is, how high does this rise? And so there are a couple of ways that you could do it. We know that you can calculate what the velocity is at this point, which is v2, right? And you know that because the pressure here would be 0. The velocity here would be 0. And the elevation here is no. So you know all three properties here. At this point here, you know it's atmospheric pressure. You know it has an elevation which is not very easy to calculate, but you know what the elevation is. It's L2 sine theta, but it doesn't matter. So you have this. And the only unknown you have is the velocity at point 2. The velocity at point 2 is a streamline velocity. And so it has components which are both horizontal and vertical. So if you wanted to calculate the height to which this rises, you could do two things. You could do it two ways. The first way is that you could write Bernoulli at points 2 and 3. And in this particular case, that would be that you know, what do you know on the right hand side? You know the elevation, Z2. You know the pressure, Z2. You know the velocity along the streamline. You know, actually it's not going to be a very easy way to do it. You know the elevation Z3, which you don't know. You know the pressure at 3, which you'd like to know. And you know the, do you know the velocity V3 at this location? You don't actually, right? So what you could, actually you do. You do. So you know that a fluid moving horizontally, coming out of here, it subscribes to Newton's, I don't know if it's first law or his third law, that a body in rest, if it's not acted on by another force, keeps on moving at the same velocity. And so you know that the velocity at point 3 has to be equal to the velocity at point 2 in the x direction. So it's moving at this velocity v2 here. It should be, it's like a ball being thrown across the room that doesn't have any drag attached to it. It's going to be going at the same velocity all the way across the room. It will also be dropping with time, but it will be going at the same velocity. So if we know that v3 is equal to this, because we know what v2 is, then we know this. We know this, and we solve for c3. That's one way to do it. What's the other way to do it? No?
Assume gravity.
Yeah, fine. Throw a ball up. You know it's going up with this velocity Vy at 2. Throwing a ball up, where does it get 0 velocity if it's acting against gravity? So you got it. Okay, so clearly I don't need to go through that. Great. And so you could also use that if you're looking at velocities in terms of, you could also do the calculation of how far this goes based on that. And so that's perhaps worth looking at. We talked about conservation of mass, and so we've dealt with this. I'm trying to think. We did talk about this in class. It's a non-steady example. I guess only making the case that if for a free jet the velocity on the surface at v1 is not equal to 0, then you don't get a free jet which is equal to 2gh square root. You don't get this. It ends up being a slightly more complicated expression, which is 2gh with some term underneath it. And so I'll move through that quickly because I can. We've talked about a free jet. Same expression. This is the control volumes. This is exactly the question that was asked. What's the difference between a control volume and a control surface? And so a control volume can deform, or it can be rigid. And so this is a rigid control volume. This is a deforming control volume, a balloon flipping through the system. I don't think you have to deal with any deforming control volumes in our particular case. Conservation of mass, well, I mean, I think we're going to run out of time and I want to move on to something else. This is the expression we had for conservation of mass, and we went through a couple of examples. And I guess the examples were ones where we looked at this accumulation term on the left hand, these two accumulation terms on the left hand side. And in the cases where we dealt with that, you can imagine two different conditions. One where you cap off a control volume and you put fluid in at some rate, in which case, by definition, the volume of the control volume is not changing with time. And so in that particular case, this has to be equal to 0, and you lose this term. But the rate of change of density in this has to respond to that. And so in other words, solving this, you have a mass flow rate into the system, which is this term here. The mass flow rate is the velocity in, the area across, and the density at which it comes in. It's negative because it's going into the system, so that's important to realize there. And the volume of the control volume is exactly this, and the only thing that's changing is a density. And so you can manipulate that to be able to solve for the magnitude of how the density changes as a function of time, just a linear function. In the case where you have the opposite, so the case we just looked at was one where the volume doesn't change, but the density does. So the opposite, I suppose, not I suppose, the opposite is the case where the volume is not constant, the density is constant. So the density is not changing with time. Get rid of this term, and this is the only one that's left. And that would be the case where you have, say, water filling a tank. This is rising at some velocity. So clearly the control volume, which is given by this area under here, is not constant with time, because this is a fluid, and the density of a fluid doesn't change very much with pressure. Pressure is increasing slightly as it gets higher, but inconsequentially, then this term gets dropped out. And again, you can solve for this system by looking at the components. Again, the flow rate into here is a negative flow rate because it's mass rate in, and the rate of change of volume is moving at the rate at which this surface is moving up in the system. And you can relate this change in volume to an area times the height. So clearly the volume of this is equal to the cross-sectional area at the bottom multiplied by the height, and the rate of change of this volume is just the derivative of this. Area is not changing, but the height is changing. And so by using that in this expression, you can just manipulate it. So I don't want to overemphasize that either, because I think the conservation of mass things you have to do are relatively straightforward. So, conservation of linear momentum. This is the same expression that we talked about before. We resolve it in the directions of the x, y, and z. We used a slightly different expression, which I think is worthwhile noting. We used this expression just to be consistent. So it's really the same as this, except this term here, importantly, is this. So if the velocity of the control surface is equal to 0, then this just converts to being the fluid flow rate across the boundaries, right? If this term is 0. But it might be important to include that. Pretty sure we went through an example about this. You need to be able to, I'll just quickly mention the fact that you have to be clear about these flow rates. These flow rates are, these flow rates are relative to the coordinates. And this flow rate is positive out and negative in. And so when you do these calculations, you have to be able to account for that as to what's going in. So here, this is a positive velocity. It's going into the system, and so it would be a negative mass flow rate. So the mass flow rate going into here would be negative because the outward normal is in this direction, but the velocity that's used here would be a positive velocity. The jet coming out of here is in the negative direction, if this is x and y. It's in the negative direction, and therefore this velocity would be a negative value. It's coming out of here, so the mass flow rate would be positive. Pretty much certainly all the calculations you have to do in this test are x and y. No angled ones. So you don't have to worry too much about that. And so there'll always be +1 or -1 or 0. Right? And so this was on the test last year. It won't be on this year. But it's important I will reiterate, to use this expression in your mass flow rate terms. So for this, if it's static, so say if you had the example that you have here, that you have a velocity, what you need to do is you need to resolve forces in the x direction, which means you resolve mass flow rates multiplied by relative velocities and the control surfaces, CS's, also in the x direction. So in this case, if you're looking at what it does horizontally, then you only need to resolve in the x directions. So what you can do is that these forces would be positive in the coordinate directions. And so if you look at the fluid coming in at some velocity w relative to this vane, and going out w out with components in each of these directions, this would be z, and this would be x, then the mass flow rates have to be the same going across this boundary as they are in and out. But the velocities that you'd use in this particular case, if it was anchored, then this value would be 0. and you can presumably solve then for knowing what these mass flow rates are relative to control volume. You can solve for the force that has to be holding it there. I guess that's an important consideration. Or if it's released, then by definition the force in the x direction, for instance, has to be 0, and you can look at the relative components of this. And so the two n-member cases that you have are either you're holding this thing in place, in which case there'd be a finite force that you have to apply, and if you're doing that, by definition the control surface is equal to 0, and you can solve for the force because you know all of these parameters. You know the relative velocities because stuff's coming in and going out. You know the true velocities of those relative to the coordinate systems, and you can calculate everything to solve for the force. Or you can release it, and if you release it, by definition the force is 0, and you can solve for the case when this is going to be equal to 0. So in other words, it has to be a specific example of these two components here. Okay? Questions? Yep.
Can you get back up to the one that had like what is the U and the 5?
U-bend?
Like, the 5 is.
Conservation of momentum. The 180-degree bend.
Yeah.
Yep.
How do you know if the pressure is positive or negative? Like, you're gonna have pressure down there where the water goes in.
Well, this pressure is higher than atmospheric because it's driving flow. So this would be a positive pressure. And relative to atmospheric, this would be 0 pressure because it's coming out of the nozzle.
So that's gonna be positive.
Yeah.
You
It's gonna be-
assume that if it's not in the same direction as the velocity is positive.
I don't know that you can solve this if you don't know what that fluid pressure is in this particular case. So you need to know, yeah. If it's going from upstream to downstream, it has to be higher upstream than downstream. But you'd probably be given the pressure.
Yeah, seriously, because on the homework, we had to do like resolve forces, we do like pressure common area. Some of them were negative, so what if that were negative?
Okay, yeah. So the pressure will be positive, but if you resolve it into a force which is acting, then in this case you define a control volume. The pressure is acting on this control volume, so this is the bend. Okay. So in this particular case, you don't have a pressure here, but you have a pressure acting here. So the pressure here is positive, but the force due to that pressure, uppercase P, which is equal to fluid pressure times area, is a vector. If the coordinate system is x in this direction, then this is a positive force. If it was the pressure and your control volume was acting in the opposite direction, it would be... So yeah, so the pressure is always going to be positive. The force that results from it depends on how you cut the surface and where it acts.
That's wrong.
Okay. Good question.
When you sum it up, don't you have both pressures and areas being positive? You're moving that way, one of them negative.
This pressure would be positive acting on, in the x direction, it would be a positive pressure force. This pressure, if it was different from 0, would be a positive force acting also in a force which is positive. But this pressure here is 0, and therefore 0 pressure times any area is 0.